Atoms. We can't get enough of them. Wherever we travel, in the city, even to outer space, they surround us. Everything on Earth, from trees, lions, birds, clouds, and gorillas, buildings, rocks, more clouds, and even humans, they are all made up of atoms, bonded together to form each and every wonderful thing that exists. In this video, we will learn all about these bonds, these exceptionally crucial atomic bonds that help keep everything we know together. This is chemical bonds. This is an atom. Every atom wants to be stable with a full valence shell. This lets them achieve noble gas configuration and complete the octet rule. Elements have different properties which change as you move along the period, the row of the periodic table, and down a group, the columns of the periodic table. These trends are known as periodicity. These arise from the orderly changes in the number of protons, neutrons, and electrons within the atoms of different elements. This in turn affects their structure and how they interact with other atoms. The one we'll be focusing in this video is electronegativity, which is the ability of an atom to attract electrons. This increases across a period, which is a row, and decreases down a group, the columns in the periodic table. Electronegativity also determines the bond of the atoms, so we'll be focusing on it in this video. Ionic bonding is a transfer of electrons from one atom to another, forming an anion, negative, and a cation, positive ion. This bond occurs between a metal and a non-metal. This is better shown with the Lewis dot diagram. Ionic bonds result in the uneven distribution of electrons, often due to the difference in electronegativity. Due to metals and non-metals having large differences in electronegativity, the non-metals literally take the electrons from the metal atoms. To determine the charge of an atom when it becomes an ion, we can look at the periodic table and see how many electrons the element has in its valence shell. To become an ion, the atom needs to fill its outer shell by receiving more electrons or taking them away. Due to this happening, the charge of the atom changes, becoming more positive, cation, with losing negative electrons, or becoming more negative, anion, when gaining more electrons to fill this valence shell. To show the amount of each element in an ionic bond, you take the calculated ionic charges and make a crisscross to write the ionic bond. For example, calcium and fluoride have the charges positive 2 and negative 1. So we do this method and give the 2 to F and the 1 to calcium to get CaF2. Then to name this ionic bond, the name of the cation comes first, followed by the anion, which has an "ide" after it, such as potassium bromide. We also write ionic bonds with the empirical formulae because it simplifies the atoms for better calculations. Covalent bonding is the sharing of electrons between atoms. This means that they can both reach their full valence shell to become stable. This occurs between two nonmetals and occurs due to the very small difference in electronegativity. They don't have the strength to take an electron off the other, so they just share them. Even though they share the electrons, each side often has a different strength of attraction, different electronegativities, meaning one may pull the electron more towards their positive nucleus. These covalent bonds are either considered to be polar or non-polar. Non-polar covalent bonds have an equal sharing of electrons. This is due to the differences in electronegativity being very, very small, meaning there is an equal pull from each side. Examples of these include diatomic molecules, which are two of the same element such as H2. Polar covalent bonds have an unequal sharing of electrons. They have a difference in electronegativity between the atoms, although it is not strong enough to be an ionic bond. The atom with more electronegativity pulls the shared electrons closer to its nucleus, while it still shares it with the other atom. This creates one side of the bond having a slightly positive and the other side a slightly negative charge due to this slight unequal sharing. Covalent bonds use the exact molecular formulae because they are not continuous. To name covalent bonds, you also keep the "ide" after it, but also these prefixes to show the amount of each electron, except you don't say mono when it's the first cation. Covalent bonds don't only exist as molecules and can also have a lattice structure. This means the pattern can continue infinitely in the lattice shape. Like ionic compounds, they are written in the empirical formulae because they could have infinite possible representations otherwise. Two good examples of covalent lattices are diamond and silicon dioxide quartz, which are natural crystals. Covalent lattices cannot conduct electricity due to their electrons being used by the bonds already and cannot flow freely. There is an exception of graphite because its lattices are in sheets, so the electrons can flow between them. Covalent lattices are very hard due to their strong bonds in their three-dimensional network. Metallic structures are formed from metallic bonding. These lattices have extremely high boiling points, except mercury due to the big amount of energy needed to break their bonds. The electrons of metallic bonds surround the positive metal ions in a sea of delocalized electrons due to the low electronegativity of metals. These are all the valence electrons from the atoms and were then released when the atoms became stable in the reaction. These electrons are also not bound to any one atom, so they can move freely between them. Because the electrons can move around very easily, metallic structures are very good conductors of both electricity and heat. These are some examples of metallic bonds. Since they are lattices, they can also theoretically continue forever. The lattice structure also allows them to be very ductile and malleable, be able to be bent and pulled into wire. This is very difficult to do with the more brittle nature of both ionic and covalent bonds. Thank you for listening. See you next time.